Welcome everyone, I am Dr. Manoj Kumar Sharma, Associate Professor, ITS College of Pharmacy, Muradnagar. This is the lecture number 19, continuation of the non-parametric test. So, it is the part 2 of the non-parametric test. The course of this lecture is Bachelor in Pharmacy and the subject is Biostatistics and Research Methodology. The code is BP801T and the university is Dr. APJ Abdul Kalam Technical University, Lucknow. So, in this lecture I explain about the Kruskal-Wallis test and the Friedman test. These are two non-parametric tests. First, the Kruskal-Wallis test. The Kruskal-Wallis test, it is a non-parametric test, and in this test we comparing the central location for k populations. We remember in Kruskal-Wallis test we compare the central location for k population. So, when we have more than 2 groups we apply Kruskal-Wallis test, and for the 2 groups we apply Mann-Whitney U test. For when we have 2 independent groups, Mann-Whitney U test, and when we have more than 2 independent groups we apply Kruskal-Wallis test. So, in Kruskal-Wallis test we compare the central location of k population, and it is a non-parametric test and it is the alternative of one-way ANOVA or one-way analysis of variance, in which we used F test. As we know, in parametric test for 2 independent groups we apply T test, and for more than 2 groups we apply one-way ANOVA. So, in parametric test for 2 groups the alternate of T test is Mann-Whitney U test, and for more than 2 groups we apply in parametric test one-way ANOVA, and Kruskal-Wallis test is the alternate of one-way ANOVA. The key concept: the Kruskal-Wallis test use ranks of data from 3 or more independent sample to test the null hypothesis that the sample came from population with the equal median. That means, in this we compare the medians of the all groups. Data is collected from k population. The sample size from population I is n I for example, and the data from population I is x 1, x I 1, x I 2, x I 3, x I k, and at last x I n I. So, where I is 1 to k, k is last small k is the number of population. Then the computation of the Kruskal-Wallis statistic, we group the n equal to n 1 plus n 2 plus n k observation from k populations together and rank these observations from 1 to n. Let R I j be the rank associated with the observation x I j. Handling the tied observation, if a group of observations are equal, the rank that would have been assigned to those observations are averaged. That means, when we have more than 2 or more ranks for same value, then we rank are tied and we find the average rank for that value. The computation of the Kruskal-Wallis statistic, let R I is the mean, which will equal to R I 1 plus R I 2 and kth observation, and last is R I n I divided by n I, where n I is the sample size, and it will be equal to. So, R I bar is the average rank for the ith sample. So, we find the average rank for each sample. Then we find the R bar, which will be equal to the average rank for all observation, and it will be equal to 1 plus 2 for up to kth and so on, and up capital N divided by capital N, and as we know 1 plus 2 plus 3 up to n, this is the sum of natural numbers. So, it equal to n into n plus 1 by 2, as this is equal to n into n plus 1 by 2, this is the sum of n natural numbers and divide by n. So, when n, this will be cancelled and the result is n plus 1 by 2. So, R bar, that is the sum of average rank for all the observation, will be equal to n plus 1 by 2. If the k population do not differ in central location, then R 1 bar, R 2 bar up to R k bar should be approximately equal. So, be noted, if k population do not differ in central location, the R 1 bar, R 1 2 bar up to R k bar should be approximately equal and close to R bar, where R bar is the sum of the all ranks of all observation, all samples. The formula for Kruskal-Wallis test is k equal to 12 upon n into n minus 1 summation I equal to 1 to k n I in bracket R I bar minus R bar whole square, and we simplify it as 12 upon n minus 1 summation I equal to 1 to k u I square upon n I minus 3 n plus 1 whole square upon n minus 1, where u I equal to the sum of rank of ith sample, that means R I 1 plus k up to R I n I, that is if u I is the sum of the ranks of ith sample. So, we and then we and summation u I square, that means first sample u I, that means first sample rank square divided by size of sample, that means we u I equal to sum of, here as you see, sum of all ranks. So, if for u I is summation sum of all ranks I equal to 1 to k, u I equal to j equal to 1 n I R I j equal to R I 1 plus k plus R I n I. So, this is the sum of the ranks for the ith sample, and summation u I is the sum, u I square is the sum of all sum of ranks of all samples, where here small n I is the size of sample and n is the total number of observations. The Kruskal-Wallis test, the null hypothesis is the k population has same central location or median, and the alternate hypothesis for k population have different control location or different median. That means, in null hypothesis we consider the median of first sample equal to the median of second sample equal to the third sample and so on, while in null hypothesis it is the opposite to the in alternate hypothesis it is to the null hypothesis, and we consider there is a difference between the central location of the population. That means, median of first sample is not equal to generally median of second sample or third sample, and the third step is level of significance, and the alpha is 5%. After applying the test statistic, we find the value of k, and if the our calculated k is greater than the tabulated value, then we reject the null hypothesis, as here the chi square. So, if k is greater than chi square at given level of alpha with degree of freedom k minus 1, then we reject the null hypothesis and the inference is there is a significant difference between the central locations of the k population. For example, in this example we are measuring an enzyme level in 3 groups of patients who have received open heart surgery. So, we have 3 groups of patient and we classify the patient in 3 groups on the basis of their age. The first group age has 30 to 45 age, second group has 46 to 60 age years and the third group have more than 61 years. So, we classify the patient on the basis of their age and we measure the enzyme level of the patients who have received open heart surgery. So, age group we have 3 population, group A, this is group 1, group 2, group 3. So, as we have more than 3 groups, so we apply here Kruskal-Wallis test and this is the enzyme level and be remember it is not necessary the subjects are equal in all groups, that means that it is not necessary the sample size of the all groups should be equal, it may be not equal. For example, you see here in first group 4 patient, in this group we have 1, 2, 3, 4, 5, 6, 7 and in this 1, 2, 3, 4, 5. So, the sample size of all 3 groups are not equal. So, it is not necessary the sample size should be equal, we apply for unequal sample size. So, how we solve this? First we assign the ranks for each sample. You see here in all the values when we assigning the rank we consider all the values, be remember not for 1, 2, 3 like this or 1, 2, 3 like this. We first see which is the minimum value in all observation. So, we assign the rank in continuation. If we see here 70.2 is the minimum. So, we assign the rank first, 70.7 is next upper value. So, we assign rank 2 and then next number is 81.3 and next number is 84.3 and the next number is 118.9 and we assign the rank for all 3 population. I again tell you that when we assigning the rank, we assigning the rank for all values for all samples in continuation mode, not for assigning rank for each population. Okay. Then we find the sum of the ranks, this is U1, as you know Ui is the sum of the rank for ith sample. So, U1 is the 51, U2 is the 32, then U3 is the 37. After summation of the rank, we apply this formula k equal to 12 upon n minus 1 summation I equal to 1 to k ui square upon n I minus 3 n plus 1 whole square upon n minus 1. So, as you see here we want to find summation I equal to 1 to 3 because we have 3 population ui square upon n I and this will be equal to the first is u1 square upon n1 plus u2 square upon n2 plus u3 square upon n3 and the u1 is in our example is you see here u1 is 51. So, we put here 51 square and the sample size is you see here 1, 2, 3, 4. There are 4 samples. So, we put here 4. Now, we put u2 square U2 is 32. So, we write here 32 square and the sample size for this is 1, 2, 3, 4, 5, 6. So, you put here 6, then U3 is 37, U3 is 37 and the sample size is 1, 2, 3, 4, 5. So, we put 37 square upon 5 and on solving all these value we find value 1094.717 this term. So, this is the value of this and n, capital N is the total number of observation in our sample. So, you see here the total number of observation is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So, we put capital N equal to 15, capital N equal to 15, then 15 minus 1 that is 14 and the value of this we have already find this and we 15 plus 1 that is 16 square and 15 minus 1 and on solving this we find the value of k that is chi square and we compare it with the chi square, standard value of chi square. Since our calculated value of k is greater than the tabulated value of chi square 0.05, the standard value of chi square is this. For 5% of level and degree of freedom 2, the value of chi square is 5.99 and our calculated value k is 7.698. So, as our calculated value is this and this is the tabulated value and this is calculated value. So, since calculated value greater than tabulated value, so we reject the null hypothesis or in other words we can say we accept the null hypothesis and so the inference of this there are significant difference in the central enzyme level between the 3 age groups or we can say the all these 3 groups which have different age groups, they have different we have these 3 age groups and this is the enzyme level. So, the median of this enzyme level is significantly differ from the median of this enzyme level of this group and from this group. Okay. That means, we can interpret that the age has a significant effect on the enzyme level of the patient who have open heart surgery. This is the main interpretation of this example. Another non-parametric test is Friedman test. The Friedman test can be viewed as an alternative to a single factor repeated measure analysis of variance, or you can say when we have single factor and we apply repeated measure of ANOVA. So, the Friedman test is the alternative of this test. The test uses data from one sample to evaluate the difference among 3 or more treatment condition. We remember in this we have one sample, that means for example, we want to compare the pain of one group at different time intervals, that means pain on first day, then pain on second time interval, that means for example third day, then pain on 7th day and pain on after 15 day. So, in this we compare one sample at different time intervals. Okay. It or sometimes the test data have more different treatment conditions. So, we apply Friedman test. The data is in the form of two-way ANOVA design or randomized block design. That means, we have two factors. The test requires that you are able to rank order the individuals across the treatment, but does not require numerical scores. The null hypothesis for the Friedman test simply states that there are no systematic or consistent difference among the treatment being compared. The calculation of the Friedman statistics require one each individual or the individual scores must be ranked across the treatment condition. Then we find the sum of the ranks is computed for each treatment. A formula is used to compute the Friedman test statistic, which is distributed as chi square with degree of freedom equal to the number of treatments minus 1. The degree of treatment equal to the number of treatment minus 1. The obtained value must be greater than the critical value for chi square to reject the null hypothesis. That means, if we have our calculated value is more than the tabulated value, then we reject the null hypothesis and conclude that there is a significant difference among the treatments. First, the steps in Friedman test, we rank the measurements within each block from 1 to k, and tied observation are assigned average of the ranks they would have gotten if not tied. Calculation, we find the Ti, that is the rank sum for the ith treatment, and I equal to 1 to small k, and the test statistic F R equal to 12 upon B into k plus 1 summation Ti square and B into k plus 1, where k is the number of treatments. The H naught, we consider the k treatments are identical, that means there is no significant effect of the k treatments, and the alternate hypothesis at least one distribution is different, that means there is a significant difference in the treatment effect in all k population. At least the test statistic Friedman we know is F, then we apply Friedman FR and the level of significance is 5%, and after that if H naught is true, the test statistics has approximate chi square distribution with df k minus 1. Generally we use right tailed test, that means right handed rejection region for this. For example, a student is subjected to stimulus and we measure the time until the student reacts by pressing a button. 4 students are used in the experiment, each is subject to 3 stimuli and their reaction times are measured. Do the distribution of reaction times differ for the 3 stimuli? So, we have 3 stimuli and each stimuli have 4 subject. So, small b equal to 4 and the stimuli are 3. So, k we have population 3 population. So, we first assign the rank, the small value is 0.6, we assign the rank 1. Then be remember here we assigning the rank 1 for 0.6, then 0.8 rank 2 and so on, and we find the sum of the rank for each stimuli or each treatment. This is the 4.5 and the rank sum of this is 11 and the rank sum for this is 8.5. The distribution of reaction times are the same as we consider in this null hypothesis and the alternate hypothesis, the distribution differ in location. Now, we apply the test statistic Fr equal to 12 Bk k plus 1 summation Ti square minus 3b into k plus 1, where b is there are 3 and k is b is 4 and k is 3. So, 3 into 4 and 3 plus 1 summation T I, that means 4.5 square plus 11 square plus 8.5 square minus b 4 into 4. So, after solving this we get the value is 5.375 and this is the calculated value, and the tabulated value as we know for chi square 2 degree of freedom is 5.99 and our value to 5.375 is less than the tabulated value 5.99. So, we do not reject the null hypothesis, the tabulated value calculated value is 5.37 375. So, since 5.375 is smaller than the standard value 5.99. So, we do not reject the null hypothesis, and there is a insufficient evidence to indicate that there is a distribution in reaction times for the 3 stimuli. So, now the summary, the Kruskal-Wallis test is the rank equivalent to one way analysis of variance F test. The Friedman test is the rank equivalent of the randomized block design 2 way analysis of the variance F test. These are the main key concepts. The method can be used when the data cannot be measured on quantitative scale, the numerical scale measured is arbitrary set by the researcher, and the third is the parametric assumptions such as normality or constant variance are seriously violated. The Friedman test used for randomized block design, the response when calculated from I to k, we apply the formula, the null hypothesis equal number of treatment distribution is false, F will be unusually large resulting in one tail test. For block series of 5 or greater than rejection region, F is based on the chi square distribution, that is k minus 1 degree of freedom. Thank you.